Hi, I'm Dr. Sarah Warden. I'm a professor here at the University of Missouri, and today we're going to talk about bridge types, how they work, and how they evolved. But first, I have a question for you. Have you ever stood on a bridge and wondered, how is this thing holding me up? How do you get supported under all this empty space underneath the bridge? Well, that's what we're going to learn about today. We're going to see how bridges work. But first, let's look at some questions we're going to cover. We're going to talk about how do bridges support the load? How do they hold you up? We're going to see what are the different types of bridges and how they evolved over time. We're going to look at how bridges are designed. How do engineers actually go through that design process and determine how they want to build the bridge? And then, how do you become a bridge engineer? Okay, so let's take a look at this bridge. This car is going to cross this bridge, and watch it bending as it goes across. How does that bridge support the weight of the car? The car made it across. That's great. But how did it work? Let's figure that out. Well, in order for that bridge to work, it needs two things. One is going to be strength. The bridge has to be strong enough for the car to cross the bridge. And the other is going to be stiffness. It means the bridge can't bend too much when the car is crossing it. Strength is coming from the materials used to build the bridge. Things like the concrete and the steel in the bridge make sure that the bridge is strong enough. Whereas the stiffness is coming from the depth, the deepness of the bridge, and the shape of its members. So let's take a closer look at this strength and stiffness. Well, what happens if my material is not strong enough, if the bridge isn't strong enough? It could break. We don't want that to happen. Let's take a look at this other video where the bridge is made out of styrofoam. Oh no, the bridge broke. The material wasn't strong enough and the car didn't make it across the bridge. So bridges need strength. The other thing is the stiffness. What happens if the stiffness of the bridge is not enough? Well, the bridge can bend too much. So let's take a look at this video of a bridge that is made of something that's too flexible. Well, the car did make it across, but it kind of went into the river there. And that's not very good either. So bridges need both strength and stiffness for them to work. How do we actually figure that out? So let's look at how engineers determine the strength and stiffness. First, they use things like physics, Newton's law, and equilibrium. These are going to give us overall laws that we can govern the motion of the bridge. Then they're going to use things like math, calculus, and algebra. These are going to allow us to write equations that we can solve to figure out how that bridge is responding to the load. So let's take a look at this bridge. It has a load on it, and so it's bending. And there's two main forces going on this bridge. One is compression there at the top of the bridge. As the bridge bends down, the top of the bridge is getting pushed together. Compression is the pushing force at the bridge. The other main force we have going on is going to be tension. Tension is going to be a pulling force that is pulling apart on my bridge at the bottom. The combination of the compression and the tension is what is allowing my bridge to resist the load. So how do engineers actually find out what these forces are? Well, they use physics and calculus to find the stresses, the compression and tension in the bridge. I have more compression stress at the top and tensile stress at the bottom, and that's resisting the moment or the bending in the bridge. Now, there are a lot of equations that engineers use to find out what these stresses are, but once you solve all these equations, you come up with this one at the bottom. The stress is related to the moment and the shape stiffness of the bridge. So let's take a closer look at this equation. Well, I look at this equation and I realize the higher the moment, which is the amount of bending in the bridge, is related to how heavy that truck is, the higher stress in the bridge, right? Well, that makes sense. More load, the bridge is going to have a higher stress. But the other main component here is that moment of inertia, the shape stiffness, how that shape resists the bending in the bridge. The higher the shape stiffness, the lower the stress of the bridge. Using this very simple equation, engineers can determine how strong a material needs to be able to resist the load on the bridge. So how strong are the materials? Well, engineers do tests to determine the strength of the materials. Things like this concrete test, right? You test the concrete in compression and you load it until it breaks. Okay, now I know exactly how strong that concrete is. How strong do you think that was? Well, the load in this concrete machine was probably about 80,000 pounds. That's a lot of load. Another thing is something like this steel test. So the steel tension test is being loaded until the steel breaks too. You can see as the stress localizes in the center and it fractures right there. And there in real life. And so that tells me exactly how strong the steel is. That piece of steel can carry around 50 KSI. That's 50,000 pounds per square inch. That's really strong too. Concrete and steel are great materials. Well, the engineers actually use both in a bridge. They use concrete and steel combined together. Let's take this look at these two beams. One has just plain concrete, and this one here has steel in it. You see the concrete cracks, but it doesn't fail. The one with just plain concrete, when it cracks, it just failed. And so without the steel, it's going to fail suddenly. But with the steel, then that helps to limit the failure. Engineers like to use a combination of materials to the greatest effect. Concrete's really strong compression, steel's really strong in tension, and so they use a combination of those to resist the stresses that are in the bridge. Okay, so we talked about strength. What about stiffness? How do I make sure that bridge doesn't bend too much? Well, let's take a look at these short videos here. In these two beams, the one is being loaded the strong way, you can see, and the other is loaded the weak way. They're both deflecting a lot, but one carries almost twice the amount of load at the same amount of displacement. And that's all because of the shape stiffness. Same size member, but loaded differently. Because that shape is different between how they load it, then one's going to be stronger than the other. Well, what if you don't use a rectangle? You don't have to use a rectangle. Engineers actually like to use this I shape. This I shape puts more material at the top and the bottom of the bridge and gives me a higher amount of shape stiffness, a higher I, for the same amount of material. It works great. Okay, so how do you actually find that deflection? Well, there's a little more physics and calculus involved to determine the equation for deflection. But once you get through all that, you find out some really important things about deflection. One, the higher material stiffness, that E is essentially material stiffness, the lower the stress. Say if you had a bridge made out of concrete that's really strong and stiff versus something made out of styrofoam. Well, concrete's going to have a higher material stiffness and therefore less deflection. Shape stiffness is also important. If I have something with a higher shape stiffness, I'm going to lower my deflection. Something that is deeper, that has a higher I, is going to have less deflection. The length of the beam, though, the longer the beam, the more deflection. The longer I get that beam, much, much higher deflection. And of course, the higher the deflection. Now that engineers have our equation, we can see the effect of all these different parameters and determine exactly how strong that bridge needs to be. In fact, they don't use just those equations. They use computer programs to do all this and calculate the entire bridge. So this is a very simple bridge, and you can see the stresses along the bridge, the compression at the top, and tension at the bottom, and the distribution of those all throughout the bridge. In fact, you can also draw little arrows on those and show which directions those stresses are going. Engineers are running analysis like this, and they check two things. They're checking the stress. They may want to make sure that the maximum stress is less than the material strength, so that when they load the bridge doesn't break. The other thing they're going to check is the deflection. They want to make sure the deflection is less than allowable. There's only so much bending you want in that bridge. If the deflection's okay, then the bridge design is good. Okay, so now that we know a little bit about how bridges work, let's take a look at each of the types of bridges and see how they actually work. Well, the first one we're going to look at is the beam bridge, the same type we've been looking at already. Beam bridges are simply a beam. It's usually one or perhaps multiple members used to span a gap in a straight line. They use that compression and tension to resist the loads. Beam bridges are extremely common today. Most of our bridges, in fact, are beam bridges. Things like this pre-stressed concrete girder bridge is going to be a beam bridge. You see how they use that I shape to maximize that shape stiffness? That makes sure that the bridge is really strong, really stiff, and weighs less and costs less as well. You can also make bridges out of steel. This is an example of a modern steel girder bridge. You can see again how we use that I shape to maximize the shape stiffness of the bridge. In fact, the new bridge going over the Missouri River is going to be made of steel plate girders and pre-stressed concrete. They are some of the most common types of bridges we see today. Let's take a look at the picture of the construction. Here's the pre-stressed concrete girders going in, and here are the steel plate girders going in. So let's take a look at some of the other bridge types that are out there. One of those is going to be arch bridges. Arch bridges are one of the oldest bridge types that are out there. Ancient people didn't have the heavy machinery like you see in the picture here. You see these big cranes? they can lift the heavy beam pieces into place and build the bridge. But they couldn't do that. So they had to come up with another type of bridge so that it can build the bridge piece by piece. And by joining all the little pieces of masonry together, they can build that bridge. But if they try to do it with the beam shape, it wouldn't work. Let's take a look at this video. Right? It didn't work. In that beam shape, the bricks separated and fell into the water. So what did the ancients do? Well, they came up with a way to make use of the strength of the masonry. Masonry is really strong in compression. So you can push it together, it can carry a lot of weight. But in tension, not so much. If you pull on it, it's going to break apart. So they designed the arch shape so that the bridge is going to be mostly in compression. So let's say I have a bridge like this. Here's my truck going on the bridge. That arch shape is allowing the compression forces to travel down into the supports and support the load, mostly in compression. Let's take a look at this video and see if the truck makes it across. Hey, it made it across. Same Lego bridge, actually same number of Legos, but with that arch shape, the truck is able to make it across. Actually, engineers can do analyses of arch shapes as well. And you can see lots of compression here, just a tiny bit of tension here, but mainly these compression forces going all the way down into the support. The arch shape makes use of that compression throughout the bridge to keep it really strong and support the load. In fact, there are lots of examples of arch bridges even today, ranging from ancient times like the Roman aqueducts to this masonry bridge or even some modern concrete arch bridges. So let's take a look at another type of bridge, the truss bridge. Truss bridges use trusses, essentially, to withstand the forces. What that does is allow me to put that compression force way up top, high on the bridge, and that tension force way down in the middle. Because I'm separating those tension and compression forces, that's actually greatly increasing the shape stiffness of the bridge. And I use these diagonal members along the bridge to connect those tension and compression forces. But you want to make sure the connections are strong, right? You want to make sure the joints don't break, and also the members themselves don't buckle. And so truss bridges, really good at separating that compression and tension, working like a beam bridge, but can have failures at the joints or in the members. Let's take a closer look at truss bridges. Why do they tend to use that triangle shape as opposed to, say, a square or a circle? Well, triangle is actually one of the strongest structural shapes. If you push on a triangle, the force is going to go straight down the sides of the triangle and into the supports. That works really well. If I pushed on this square, what do you think would happen? The top bends and it can actually slide over. Well, that's not going to work. And if you push on this circle, what do you think? Well, it's just going to squish, right? And so triangles are going to give us the best shape. And so truss bridges are essentially a series of triangles. Look at all these different truss bridges, these different configurations of trusses you can have out there. Lots of different configurations, lots of different ways to withstand the load using that shape of triangles repeated over and over. Let's take a look at this quick video of a truss bridge. A car is going to cross it, and you can see the compression there at the top in red and the tension at the bottom, and the car makes it safely across. Now, if I change the members of the bridge and perhaps I reduce the sizes, well, oh no, it didn't work. The member itself buckled. And so in truss bridges, they're only as strong as the individual members and the joints or the connections of the bridge. There are lots of examples of truss bridges even today, such as the Missouri River Bridge in Rocheport was an old truss bridge. Then another one in St. Louis, and this one in St. Louis here. Truss bridges used to be a very common type of bridge for some of those longer spans. But because of the labor required to join all these little tiny truss pieces together, they're becoming not quite so popular. And so most bridges, such as this I-70 bridge when it's getting rebuilt, is being replaced with a beam bridge. Okay, so what if you have a really long span? Well, then you might go into cable stay or suspension bridges. These are some of the longest bridges in the world. they can make use of high-strength tensile wires to build these really long bridges. Look at these wires. The wire might be only 0.2 inches in diameter, but can hold 8,000 pounds. That's like the weight of 2 cars. This is a picture of the Golden Gate Bridge. You see how big that cable is in the bridge? Imagine how much load it can carry if just one individual wire, the size of your pencil, can carry 8,000 pounds. It's a lot of load. Well, suspension bridges use the idea of carrying a load that's going to go up the suspender cables and down into the main cables and into the supports. So if the car is here like this, the load's going to travel up and across and then down. So suspension bridges make use of the shape, this catenary curve, that puts all these forces in tension. And because steel is going to be really strong in tension, you can carry a lot of forces, and then it goes into the concrete supports here that take it down into the foundation. There's lots of examples of cable stay bridges around. The Stan Musial Bridge in St. Louis, the Golden Gate Bridge, of course, and the longest bridge in the world, over 6,000 feet long, over in Turkey. That's a really long bridge. Okay, so now we learned some bridge types. Some beam bridges, we have arch bridges, we have truss bridges, and we have cable stay and suspension bridges. But how do you decide which one to build? Which one is going to be the best bridge for a particular application? Well, that's what the engineer does. They have to make use of their engineering knowledge and the conditions at the site to determine which is going to be the best type of bridge. So, how do engineers design bridges? Well, let's figure that one out. In bridge design, remember we had 2 things that were requirements. You have to have strength and you have to have stiffness. Okay, the bridge has to work. We just learned about how the bridges work. In order to determine the strength and stiffness, engineers use codes and standards. Things like the Bridge Design Code and standards like a standard for steel construction is going to give the engineers the equations they need and the expected loads on the bridge to make sure the bridge is going to be strong and stiff enough. There's actually other things that are nice to have in a bridge. Things like aesthetics, that make sure it looks good. Cost, that's probably one of the most important things. The bridge has to be able to be built for a reasonable amount of money. Materials, what's available. If you have something easily available at the site, it's going to cost less. Sustainability, is it going to be good for the environment? Are you using sustainable materials? And constructability, can it actually be built with the conditions at the site? Engineers have to weigh all those things and determine what's the proper balance. These nice to have, well, it might be more constructible this way, but it's more sustainable this way, and they have to figure out what's the balance in that to determine what design of the bridge. But they always have to make sure that the bridge is strong enough and is stiff enough. The bridge has to work. So let's listen to bridge engineer Brandy Baldwin as she explains how the new bridge in Rocheport is going to work.
Hi, my name is Megan Best, and I'm a student at the University of Missouri. And this is Brandy. Could you tell us a little about yourself?
My name is Brandy Baldwin. I'm one of the engineers for MoDOT.
Why do we need a new bridge over the Missouri River?
So we need a new bridge here over the Missouri River because this structure that we have existing is aging, and it does need some new work in the very near future. So we're trying to get it done before we need to do that work. That work that we needed to extend its life cost about $30 million and was only going to get us about 10 more years. So we took that money and put it into this new bridge, and we're getting a bridge that's going to last us almost a century.
So could you explain a little bit about the general process design of the bridge? Like what are the most important things to consider when you're designing it?
So a lot of the things we consider when we're designing a bridge, the very first things we look at is how much traffic is going over the bridge. What is the bridge crossing? Are we crossing a body of water? Are we crossing traffic? Or maybe just a dry creek bed? And then there are other things to consider, like the bridge type that we're going to be designing. And can we build the bridge in the same location that it is in? And you also need to think about the subsurface conditions, because a lot of bridge you can't see from the surface. It's underneath the ground level.
How do you know if the bridge will be strong enough?
So there is a lot of engineering analysis that goes into determining how to design a bridge and know if it's going to be strong enough. So we do lots of calculations. There are lots of engineering code and specifications that engineers and designers have to follow. And they follow those written rules and use a lot of math and science to figure that out.
Okay, thanks, Brandy. So, how can you become a bridge engineer if you're interested? Well, do you like solving problems? That's like the number one requirement of an engineer. You have to like solving problems. You have to like figuring out how things work, how to make them better, and how to build them. If you're somebody who likes to solve problems, then you can be an engineer because engineers are going to be problem solvers. So you can be an engineer. Okay. Other skills that engineers might have would include things like good at math and science. Math and science is important. You need to be okay at it. You don't have to be extremely good, but you have to be able to converse in math and science because all about how that bridge works was using things like physics and calculus. And so you kind of have to understand that. But also things that are really important in an engineer is good at creative thinking, coming up with new ideas. How are we going to get this thing built? There's always new innovations in engineering, and being creative helps you with that innovation. Great communication skills. You need to be really good at communicating and talking and in writing. Building a bridge requires a huge team of people, and they all have to talk to each other to get that bridge built. You also have to be able to organize and make connections. So you have that huge team of people, they have to be able to work fluidly together and know what they're doing at each point in time. You need to get along well with others, and you need to be determined to get things done and do a good job. And finally, you need to have good leadership skills. You need to be able to lead that team of people so that you can get the bridge built. So let's listen to Brandy again and learn about how she became an engineer.
How did you become an engineer?
So the way I became an engineer was I saw an aptitude for myself. Then when I graduated high school and wanted to go to college, picked the civil engineering role and started taking those classes. And when I graduated, obviously you start looking for jobs then, right? And MoDOT was hiring, and I actually took a position with MoDOT as a construction inspector. Then I graduated into a promotion as a utility engineer, so there are a lot of opportunities at MoDOT. The first big bridge I got to work on was the Champ Clark Bridge in Louisiana, Missouri, which was very fun and a big learning experience. And then after that project, I moved over here to Rocheport, Missouri to help build this one. So a lot of really fun and exciting opportunities becoming an engineer.
Yeah, that sounds very exciting.
Yeah.
Why did you become an engineer?
So I, as a child, have always really enjoyed solving problems and challenging myself to figure out how things work. And one of my first memories as a kid, we had to cross the Mississippi River. And one of those bridges there, my great-grandpa actually worked on. So my parents would be like, hey kids, remember great-grandpa worked on this? And we would go visit with him and ask him stories about it. And to me, that's what I want to leave behind too, that my kids can tell their kids and their kids that, hey, grandma used to work on this bridge.
Yeah, that'd be super cool. What is the coolest thing about being a bridge engineer?
That's probably the coolest thing about being a bridge engineer. The coolest thing about being a bridge engineer is getting to actually be out here and see these things getting built.
Awesome. Thank you so much.
Yeah, thank you.
Thank you, Brandy. So now I encourage you to go out there and build a bridge. Thank you for listening, and I hope you have a great day. Bye.